Hello everyone, welcome to my presentation. My name is Tingyi Zhou. I'm a recent Ph.D. graduate from Jalali-Lab at UCLA. My research focuses on the symbiosis of physical system and AI algorithm. Today, I would like to present one of our recent work, optimization and training of the nonlinear Schrödinger kernel. This is a new computing paradigm that targets at real-time data processing in ultra-fast instrument. One major application is to act as a backend of the time stretch system. First of all, I'd like to introduce the time stretch. The photonic time stretch is a technology that can perform measurements of ultrafast signal at billions of frames per second. It works under the theory of a dispersive Fourier transform, where the chromatic dispersion in an optical media, such as an optical fiber, maps the spectrum of an optical pulse to a temporal waveform whose intensity mimics the spectrum. With dispersion, the waveform can be wide, very wide, so basically a stretched version of the spectrum. Now, if we have the information encoded onto the spectrum beforehand, it can also be slowed down during the process. One major application, which is also related to the topic today, is the time stretch microscope. Here is a short video on time stretch microscope for cancer diagnosis. In this system, the femtosecond laser pulses are spatially dispersed through a pair of diffractive gratings, becoming rainbows, so that each wavelength of the color corresponds to a spatial coordinate. The rainbow is then focused onto a microfluidic channel and illuminate the cells passing by. If we zoom in, there are two types of cells. The white one is the normal white blood cell, and the yellow one is the cancer cell. Here, each rainbow flashes on one line of the cell. This encodes the spatial feature of that line onto the rainbow, which is the spectrum of the femtosecond laser pulse. There's a reflector on the back of the microfluidic channel so that the encoded spectrum can be reflected, go back into the fiber, and enter an optical circulator, which redirect the light into a dispersive fiber. Now, in the fiber, the dispersion will stretch the pulse so that its temporal waveform mimics the spectrum. The stretched pulse is then detected by a photodetector, digitized by an analog-to-digital converter, and sent into a digital computer, which in this case, an FPGA. In the FPGA, the acquired 1D scans are reshaped to 2D images and then get classified. This ultra-fast imaging system generates terabit per second of data. This is good for machine learning algorithms, especially deep neural networks, because they require large datasets for training. However, there's a big problem. On one hand, the ultra-fast optical instruments, like the time stretch camera we just shown, can capture billions frames of data per second. On the other hand, in order to achieve sufficient accuracy, the neural networks need to be complex enough, which leads to milliseconds or tens of milliseconds inference latency. Essentially, there's a huge mismatch, an approximately 6 orders of magnitude gap between the timescale of neural nets and the ultra-fast optical instruments. And even if we can run neural nets at that rate, billions of inferences per second will have prohibitively large power dissipation, so it'll never be possible. To solve this problem, we propose the nonlinear Schrödinger kernel for accelerating machine learning data classification. This is published early last year on the Journal of Lightwave Technology. It uses an optical system to perform nonlinear transformation, which shares some similarities with the kernel trick in machine learning. The kernel trick is a common method in machine learning. It works by processing the input data with a kernel function, and then send the result to a light machine learning model. Let's look at this example. Here we have two types of data, the red one and the green one. Their boundary is highly nonlinear, therefore cannot be separated using a linear classifier. A simple workaround is to use a nonlinear function, or we say kernel, to project the data into a new space where the boundary between two classes become linear. A linear classifier would subsequently do the work. With similar idea, our kernel also performs a nonlinear projection. Here's an illustration of the nonlinear Schrödinger kernel. This technology uses nonlinear Kernel effect in an optical component, which reshapes the spectrum of a femtosecond laser pulse, performing complex transformation. In the start, we map the input data shown here as the 1D vector onto the broad spectrum of a femtosecond laser pulse, with each entry assigned to a virtual input node. This rainbow is basically the encoded femtosecond laser. It is sent into a nonlinear optical element where the complex nonlinear process governed by the nonlinear Schrödinger equation transforms the input data while reshaping the optical spectrum. The transformed data is collected by a spectrometer with the same sampling dimension as the input data. Each sampling point can be viewed as a virtual output node. The collected data is sent to a lightweight digital linear classifier. Through this process, the nonlinear transformation projects the data onto a new space, and in this space, the previously linearly non-separable data becomes linearly separable. This way, we can use a linear classifier with low computational complexity for nonlinear tasks. One thing I want to emphasize is that our kernel is not any form of instantiation of the existing numerical kernel function. It purely came from the physical system. The performance of this technique is evaluated against various datasets, and here's the results on the time-series cancer cell detection I mentioned earlier. Using a linear classifier as a baseline, we compare the nonlinear Schrödinger kernel with the common numerical kernel known as the radial basis function, RBF. They have similar accuracy while our kernel is orders of magnitude faster. This shows the great potential of this technique. However, we also observe that the performance of our kernel is data dependent. That is because there are few ways to tune this physical kernel. To make it more adaptable, we go back to the first principle. Looking at the nonlinear Schrödinger equation that governs the whole transformation, we can see this process is very complicated. There are multiple effects going on, and in order to identify the core effect, we run mathematical simulation to isolate them one by one. For the sake of time, I won't put all the results, but only the important one. We perform the simulation with the nonlinearity turned on and off. We compare the performance of both cases and the baseline obtained using a linear classifier without kernel. So clearly, without nonlinearity, there's nothing. The classification error for a linear kernel is almost the same as the baseline. Well, on the other hand, the nonlinear kernel have a obviously better classification error. On the other hand, we also discovered that the other factors such as dispersion or loss are much less effective compared to the optical nonlinearity. So in other words, the optical nonlinearity is the core. Therefore, to tune the kernel, we should focus on engineering the nonlinearity. Considering the nonlinear optical effects, such as cell-phase modulation, cross-phase modulation, and four-wave mixing, one common thing is that they are all coherent processes. This means the nonlinear process is phase-sensitive. Now, for a laser pulse with same power spectrum with a spectral amplitude, the spectral phase can greatly affect the nonlinear transformation. We use an experiment to demonstrate this. Here, we modulate 3 different phase patterns onto the same supercontinuum laser pulse, send them through the nonlinear optical element, and look at the output one by one. The data collected by the spectrometer shows that different phase patterns leads to different nonlinearity. Therefore, we can tune the nonlinearity of the kernel by controlling this phase, and we call this approach phase encoding, and subsequently, we call the phase pattern the phase code. Now, using phase encoding, we can build up a closed-loop system to optimize the performance of the nonlinear Schrödinger kernel. As shown here, the updated system has 2 parts, a tunable nonlinear Schrödinger kernel and the digital feedback loop. The tunable nonlinear Schrödinger kernel is basically the original open-loop system. It starts with a supercontinuum femtosecond laser. The input data is mapped onto the spectrum of that laser through a spectral modulator, and in the meantime, a phase code is also modulated onto the laser for tweaking the nonlinear process. The modulated laser is then sent into a nonlinear optical element and acquired using a spectrometer. In the digital feedback loop, the acquired data is used to calculate the classification error. This error is then passed to a genetic algorithm to generate an update on the phase code. This system runs iteratively until the updated phase code leads to minimum error. We demonstrated the optimization results using the time-stretched cell image data mentioned earlier. We can see that compared to an unoptimized one, the classification error of an optimized kernel is almost halved. This proves the effectiveness of this upgraded system, which now becomes trainable and therefore more general to various applications. In conclusion, our kernel enhanced classification with low inference latency. And in this research, we showed that we achieved the optimization using phase encoding with the digital feedback. This provides a general framework for adapting this physical computer to various applications. Still, I want to emphasize that the performance of this kernel is still data dependent, because after all, it is a statistical approach, just like all AI techniques. Now, this is the end of my presentation. Thanks for your watching.